All right, so this should be a pretty short correction. We just have to remember some of our long-term memory chunks, and we're good to go. So this first one, I can see it's repeated addition, and I want you to include these reasons along with me today. We know repeated addition is the same thing as multiplication. We have to remember that. Repeated addition, multiplication. So here I know x plus x is just 2x, and then a plus a plus a is 3a. So we can say all this equals all of that. 2x plus 3a. Remember, I can't add those together because I don't have 5x's or 5a's. So let's find another one that looks like this, where we can use this same reasoning. We also see repeated addition over here, so let's remember that. Repeated addition is the same thing as multiplication. So here, let's see what we've got. Well, w and w, though we can add those. Let's move those close together. Those are like each other. And then we have 3y's. We have 10 just hanging out off by itself. But here we have a total of 3w's plus 3y's plus 10. And that's as far as we go. So we also, here's a little bonus long-term memory chunk. We also remember that order doesn't matter. Order does not matter for addition as well as multiplication. So that's why I moved this w over here to be added with his friend 2w. All right, let's keep going. All right, on this one, I see repeated multiplication now. Let's remember repeated multiplication, that's the same thing as an exponent. So here I can say h times h times h. That's the same thing as h to the third power. It looks like we have an exponent for our very next one. So let's use our long-term memory chunk again. I have repeated multiplication is the same thing as an exponent. So here I can say this is the same thing as 3 times 3 times 3 times 3. Oh, and you know what? I can even make another statement here. I could say this is equal. Well, let's think. I can think, that's 9, and so is that. That's 9. So I can actually say this is 81. So here I kind of made this even better, right? 3 to the fourth power, same thing as 3 times 3 times 3 times 3 equals 81. Yet another repeated multiplication. So remember, this is repeated multiplication. Repeated multiplication, that's the same thing as an exponent. 1, 2, 3, 4, 5, 6. We have 7 5s. So this is 5 to the 7th power. So it's a little 7. So let me maybe write that a little better. My marker's a little fat here. So 5 to the 7th power, just like that. All right, before I get into our distributive property stuff, let's look at this one weird one. Y divided by 3, why that's the same thing as y over 3. And remember, anytime you divide something by 3, you're technically also multiplying by 1/3. So we can also say that's 1/3 y. Maybe this is a bonus one you might not have thought of, but that's also true as well. Dividing by 3, the same thing as multiplying by 1/3. In the same way that if we had x divided by 2, that's the same thing as x divided by 2, or the same thing as x times 1/2. The same idea. All right, now into the distributive property. So in these first two, they're already factored. We're going to expand them. So remember, distributive property means multiply outside by both inside terms. Technically, that could also mean divide here. Let's look at the multiplication. So it means this thing right here means 12 times 2 plus 12 times 3. So there's my equivalent expression, but I can also say it's 24 plus 36. You could take it a step even further, and you could say, oh, well, that equals 60, but we're just writing equivalent expressions. But I know this is equivalent to that, it's equivalent to that. These are all equivalent to each other. Why? Because of the distributive property. So this one's kind of the same idea. It means 2 times x plus 2 times 3m. So let's think about this step by step. What's 2 times x? Well, it's just 2x. What's 2 times 3m? Well, what's 2 times 3? It's 6. Let me just bring the m on there with it, and there you go. We've got 2 equivalent expressions we could have there. But this also goes backwards, right? In the same way that I can go down multiplying here, so down I am multiplying, I can also go backwards by dividing. So if you think about it, we could break these two apart. We think, oh, what number do they have in common? They have 12 in common, right? Let's see if we can do that here with 20 plus 28. So again, my goal is to try to break each of those apart with a common number. So let's try this. Well, 28, that's kind of the weirder number. It's not as versatile as this one. I know it's 4 times 7. Does either of those numbers work with 20? Yes, absolutely. 4 times 5 is the same thing as 20. So let's think where everything goes using our distributive property. We've got addition on the inside. Our common number goes outside, so I would have 4 and then 5 plus 7 on the inside. So 4 times the quantity, 5 plus 7. So if someone said, here's this chunk of stuff, write an equivalent expression for it, you would say, oh, here it is right here. Let's try one last one here for our opening problem set. It's 2x plus 4. So again, I've got to split things up here. 2x I can think of as 2 times 1x. I can break it apart, right? 2 and 1x. Let's break apart 4. So I can write 2 times 2. Where's the common number? 2. So 2 is on the outside. What's left on the inside? 1x plus 2. Or you could just have x plus 2. So you can have this right here. 2 times x plus 2. So if you weren't sure on some of those corrections, come back to the table and talk to me, and we can work through it and talk about it, and then I can send you on your way and finish the rest of your work today.